Hey, welcome back to the channel, everybody. This is Kevin. In this week's video, I want to answer a student request. I had a student about 2 weeks ago want to better understand GLBP configuration. And I looked through my YouTube videos and I did not have a GLBP configuration video, so that's what this week is all about. First, let's do a quick review of GLBP theory. Now, GLBP, the Gateway Load Balancing Protocol, that's a first hop redundancy protocol, an FHRP, meaning that if our default gateway goes down, there's going to be another gateway that can take over. That's what we have with HSRP, the Hot Standby Router Protocol, which is Cisco proprietary, VRRP, the Virtual Router Redundancy Protocol, which is an industry standard. GLBP also does redundancy. It is Cisco proprietary, but it does something beyond redundancy. As the name suggests, it does load balancing. Take a look at this topology on screen. And if you notice R1, it's going to be acting as what we're going to call an AVG, an active virtual gateway. Think about when a PC boots up and it wants to get out off of its local subnet. It needs to go to its default router. Well, it knows the IP address of the default router, but it doesn't know the MAC address. So it sends an ARP broadcast saying, hey, can somebody tell me the MAC address corresponding to this IP address? Well, the router in a GLBP group that's responsible for that is called the AVG, the Active Virtual Gateway. It responds to those ARP queries. And R1 in this example we'll say is the AVG. And a router that's capable of getting us off of our local subnet, that's called an AVF. An active virtual forwarder. So instead of having a single router that's handling the load for the entire subnet, as we do with HSRP and VRRP, we can have as many as 4 active virtual forwarders actively forwarding traffic. Now, I only have 2 on screen, R1 and R2 for simplicity, but we could have as many as 4. So both R1 and R2, they're both AVFs. So let's say that PC1 sends up a broadcast saying, can somebody tell me the MAC address of my default gateway, 10.1.1.1? Well, the response to that query is the job of the AVG, the Active Virtual Gateway. And it responds and says, sure, that has a MAC address of all ones, which is the MAC address of R1. But check this out. PC2 is going to ask the very same question. It's going to say, hey, what's the MAC address of 10.1.1.1? This time, in response to the very same question, R1 says, oh yeah, that's the all 2's MAC address. And that's the MAC address of R2. So now when PC1 wants to leave our subnet, it's going to go via R1 as its default router. And PC2 is going to be using R2. They're both pointing to the same default router IP address, 10.1.1.1, but that address is being serviced by more than one router. And when we say we're going from router R1 to R2, and we could even go to R3 and R4, by default, we're going to be using round robin. The first time we respond to a ARP query, we're going to say, here's R1's MAC address, and the next time it's R2's MAC address, and then R3 and R4, and we start all over again. But there is an option of having a host-dependent mapping, where maybe a specific host is always going to be given a specific router to handle the forwarding of that traffic. Or maybe one router is more powerful than the other router. We could weight those routers. For example, maybe one router has a weight of 100 and one router has a weight of 50. Well, in a case like that, the router with a weight of 100, its MAC address is going to be given out twice as often, because 100 is twice 50. Its MAC address is going to be given out twice as often as the router with a weighting of 50. Now that's a review of the theory of Gateway Load Balancing Protocol. Let's take a look at a video I recorded some time ago showing the configuration of GLBP. Here we've got a couple of routers, R1 and R2. We want R1 to be the AVG, the Active Virtual Gateway, that's going to be handing out virtual MAC addresses to the AVFs. Both routers are going to be AVFs, Active Virtual Forwarders. And remember that the default load balancing algorithm is round robin. Let's start off with that, and then we'll talk about how to set it up with a weighted load balancing algorithm. But to get started, we're going to go into interface configuration mode on R1 for interface fast Ethernet 0/0. And this is very similar to setting up HSRP. We're going to say GLBP. We're going to give a group number, say IP, and specify the virtual IP address, which is 10.1.1.1. And I want R1 to be the active virtual gateway. And to make that happen, I'm going to give it a priority that's higher than the default of 100. I'm going to say GLBP group number 10, priority 110. And unlike VRRP, but like HSRP, preemption is not enabled by default. I'll want to turn on preemption by saying GLBP, group number 10, preempt. And as a good practice, I'll turn on authentication. We do it the same way that we turned on authentication for HSRP. We'll say GLBP, give the group number. Authentication, and notice we can select either MD5 or text authentication. I'm going to say MD5, and now we're given the option of specifying a globally configured key chain where we can have some keys become active at certain times and other keys expire. I'm just going to give a key string, a string that's going to match on router R2. I'll say key-string, and I'll make that key string $3CR3 capital T. And I'm done with the initial configuration on R1. Let's go to router R2. On router R2, we'll also go into interface configuration mode for fast Ethernet 0/0, and I'll say GLBP group number 10 and give that virtual IP address of 10.1.1.1. And since preemption is not enabled by default, I'll want to enable that. I'll say GLBP group number 10 preempt. I'm going to leave the priority at the default of 100 because I want this to be the standby for becoming the AVG, but I need to set up matching authentication. You see that I'm getting a bad authentication error message on screen. That's not good, so we need to fix that. Let's say GLBP group number 10, authentication, MD5, and we're going to give a key string of $3CR3 capital T. Hopefully that matches. And let's give a couple of verification commands. We can see here on screen that we are in the listen state for forwarder 1, but we're active for forwarder 2. Forwarder 1 and forwarder 2, they have different virtual MAC addresses. If I do a show GLBP brief command, the first line in the output is talking about the AVG. We're saying that R2 is currently the standby for the AVG. We've got a priority of 100. The virtual IP address that we're servicing is 10.1.1.1. The active router, which is R1, is 10.1.1.2. And we're the standby. The standby is local. This is just talking about the AVG. But in addition to the AVG, remember we can have 4 active AVFs in a group. And an AVF, an active virtual forwarder, is going to be forwarding for a particular virtual MAC address. And you can see that we're currently in the listen state for this virtual MAC address, and the AVF for this virtual MAC address ending in 01, it's 10.1.1.2. That's R1. However, we are active for this virtual MAC address. You can see the active router is local, and that's for forwarder 1 and for forwarder 2. We can get more information about this by doing a show GLBP without giving the brief option. You can see for the AVG, our current state is standby. We see that we're doing authentication. We're using MD5 with a key string, and we've got the default hello time of 3 seconds and the default hold time timer of 10 seconds. The virtual IP address that we're servicing is 10.1.1.1, and our priority is currently 100. Our waiting is the default of 100. And R1, by the way, also has a weighting of 100, meaning that when the AVG is handing out virtual MAC addresses, it's going to hand out these virtual MAC addresses equally. For forwarder 1, we're currently in the listen state. We can see that R1 is active, and the virtual MAC address being serviced by forwarder 1 is this. However, we are active for forwarder 2, and this is the virtual MAC address that we're servicing, and this gives us more confirmation that we are active for forwarder 2. If we go to R1 and do a show GLBP brief, we can see that we are active for this MAC address, and we're in listen for this MAC address. Now let's see GLBP in action. I'm going to go to PC1, and right now I've rebooted this router acting as a PC, and hopefully it's not yet done an ARP for its default gateway, but I'm going to do a trace route to this IP address that we're pretending is on the internet, and this is going to cause it to ARP for its default gateway, and the output's going to show us which path we're using. And then we'll take a look at the ARP cache. But let's do a trace route to 1.1.1.1, and you'll see that our first hop, our default gateway, is 10.1.1.2. That's R1. If I do a show ARP, we can see that the MAC address corresponding to 10.1.1.1, which is configured as our default gateway, is this virtual MAC address. This is the one that ends in a 01. This is the virtual MAC address being serviced by forwarder 1. And right now R1 is the AVF servicing this MAC address. Let's go to PC2 and do the same thing. On PC2, I'm going to do a trace route to the very same IP address out on the internet, and I'm on the same subnet as PC1. Let's do a trace route to 1.1.1.1 and take a look at my next hop. It's 10.1.1.3. If I do a show ARP, it says 10.1.1.1 has a MAC address that ends in a 02. Remember, with PC1, the very same IP address had a MAC address ending in 01. This is evidence that GLBP is doing its job. Router R1, acting as the active virtual gateway, responded with different answers to the very same question. Both PC1 and PC2 said, hey, can you tell me the MAC address corresponding to 10.1.1.1? And the first time R1 said, sure, it's this MAC address. But then when PC2 asked the very same question, R1 responded with a different answer. It says, sure, it's this MAC address. This is giving us that automatic load balancing that we talked about. But of course, we get more than just load balancing. This is also giving us redundancy. Let's prove that. Let's go to R2 and let's shut down interface fast Ethernet 0/0. Let's say interface fast Ethernet 0/0. Let's do a shutdown. And let's go back over to R1 and see if it is now actively servicing those two MAC addresses. Let's do a show GLBP brief command again. And look at this. Both MAC addresses are still being serviced. We're active for both of these virtual MAC addresses on this AVF on R1. And if I go back to PC2, which had been using R2 to get to the internet, if I do a trace route now to 1.1.1.1 using the very same MAC address that I used earlier, I'm going to a different router. I'm going to R1. I can do a show ARP, and you can see this information has not changed. It still knows the same MAC address, but now that same MAC address is being serviced by R1. Let's take a look at a show command on R1. Let's do a show GLBP, and we pointed out some of these things earlier, but now notice that we are active for forwarder 1 and for forwarder 2. And also, we've got a couple of timers that we did not have with HSRP or VRRP. We have the redirect time and the forwarder timeout. Let's talk about these. What is the redirect time? The redirect time says how long an active virtual gateway will respond to ARP queries with the virtual MAC address of a failed AVF. In other words, this is the virtual MAC address of a failed active virtual forwarder. This time of 600 seconds says how long this AVG is going to be handing out this MAC address when we have hosts saying, hey, what's the MAC address for 10.1.1.1? And we've got this other time, the forwarder timeout, and this says how long a backup AVF, which is R1 in this case, it says how long a backup AVF is going to accept frames destined for this virtual MAC address of a failed AVF. In this case, how long is R1 going to accept frames destined for this virtual MAC address? And you see the default is 14,400 seconds. That's 4 hours. Hopefully the device is pointing to that virtual MAC address of the AVF that has failed will, in the meantime, send out another ARP and be given another MAC address. So we don't have to keep servicing this MAC address for this failed AVF, but we will for a while in anticipation that this AVF might be coming back up. Let's repair things now. Let's go back to R2 and we'll go back into interface fast Ethernet 0/0. Let's bring it back up. Let's do a no shutdown. We'll put things back the way they were. And let's talk a bit about load balancing. Right now, we're doing round robin or equal load balancing. The first ARP request that comes in, the AVG might say, use the virtual MAC address of R1. And then for the next ARP request, it says, use the virtual MAC address of R2. And then it goes back to R1 and then R2. Back and forth, an equal distribution of these virtual MAC addresses. But in the real world, you might have a more higher powered router. You might have a high powered multi-layer switch that supports GLBP. And you want it to get the bulk of the traffic. You want to hand out its virtual MAC address more often than you hand out a virtual MAC address for another router, which might be a lower powered router. What we can do to influence that is to adjust the weight. Currently, each of these routers have a default weight of 100. We can change that though. Let me show you how we can mix this up a little bit. We can go into Fast Ethernet 0/0 on R1, and let's say that we do not want to hand out R1's virtual MAC address as often as we're handing out R2's virtual MAC address. Here's what we could do. We could say GLBP, group number 10, and then say weighting, and I could give a value. I'm going to say that my weight is 50. And I could go to R2 and say, your weighting is 100, but actually it is already 100 by default. And if we enabled the weighted load balancing algorithm, which I'm not going to do in this example, we're going to continue to use round robin. But if I wanted to do that, we could use the command GLBP, give the group number, and then say load-balancing weighted. And if we did, we would be saying that we would want router R2's virtual MAC address handed out twice as often as router R1's virtual MAC address, because 100 is 2 times 50. And we talked about interface tracking and object tracking earlier. We can actually mix in object tracking with this weighting. Let's go take a look at this on router R2. This is kind of interesting the way this works. On router R2, we know that we already have a weight of 100. If something happens to this router, maybe an interface goes down, maybe a route disappears from the IP routing table on this router, maybe the metric of a route in the IP routing table gets too high. There are reasons why we might not want to hand out the virtual MAC address of this router as often. What we could do is reduce the weight based on network conditions. In fact, we could reduce the weight down to a point where we don't want our virtual MAC address to ever be given out. Here's what we could do. Let's go into interface Fast Ethernet 0/0, and we've already got a weight of 100, but I'm going to add a couple of thresholds to that. I'm going to say GLBP, group number 10, weighting 100. We have that by default, but now I'm going to say lower, and I'm going to specify a low watermark threshold, and I'll just say it's 50. And I'm going to specify an upper threshold, and I'll make it 80. Now what's going on here? I might say that based on network conditions, I want to reduce the weight of this interface by a certain amount. And I'm saying if I drop below 50, not if I equal 50, but if I drop below 50, then I no longer want to be an active virtual forwarder. My weight is too low. Do not hand out my virtual MAC address. And if network conditions improve a little bit, it might creep up above 50. Maybe it gets up to 60 based on network conditions. But if I drop below 50 and I'm no longer an AVF, just going a little bit above 50 is not going to suddenly make me an AVF. Once I drop below 50, I then need to exceed my upper watermark. I need to exceed 80 to once again be an active virtual forwarder. And I think that's a good thing, because otherwise we might have a flapping route. We might have a condition where suddenly we're bouncing back and forth between being an AVF and not being an AVF, back and forth, back and forth. We don't want that. It's nice to add this little buffer in here. So now I'm saying I've got to go back above 80 before I will regain my role as an AVF. And now let's see what we could do to reduce that weight of 100 based on changing network conditions. What we can do is use object tracking. Let's go create a tracking object. And even though GLBP does not directly support interface tracking like HSRP did, it can, like we saw with VRRP, have an object that tracks an interface state. So we can really essentially do interface tracking. Let's set up a tracking object. I'll say track1, and I'm going to track interface serial 1/0. That's my serial link going out to the internet, and I want to track the line protocol of that interface. Now let's go back into interface configuration mode for Fast Ethernet 0/0, and let's say GLBP group 10, weighting, and I'm going to reference tracking object number 1. That's checking on the line protocol state of serial 1/0. And I'm going to say if that tracking object goes down, I want to decrement my weighting, which is currently 100. I want to decrement it by 51. Taking 51 away from 100 is going to make me drop below that low water mark of 50. If I just decremented by 50, that would not be enough. I've got to actually drop below that number to say I no longer want to be an AVF. I'm going to say let's decrement my weighting by 51 if serial 1/0 were to go down. Let's enter that. Let's test it now. Let's go into interface serial 1/0, And let's shut it down. By doing this, the tracking object is going to go into a down state, and when it goes into a down state, that's going to cause the weighting on Fast Ethernet 0/0 to be decremented by a value of 51. We're reducing the current weight of 100 by 51, which is going to give it a new weighting of 49. And based on this command, if we're lower than 50, then we no longer want to be an AVF for our virtual MAC address, and we're going to transition out of that role. In fact, you just saw it happen on screen. You can see for Forwarder 2, we just left the active state and went into the listen state. And as a result, if I do a show GLBP brief command, you can see that I am no longer active for my virtual MAC address. And instead, if I do a show GLBP brief on R1, it's active for both virtual MAC addresses. And we can see in the output of the show GLBP command that our current weighting is 49. We're configured for 100, but we're currently 49 because tracking object number 1 is in a down state, and that caused us to decrement our weighting of 100 by 51, which dropped us below this threshold, causing us to take ourselves out of the AVF role. Let's fix that. Let's go back into interface serial 1/0. We'll do a no shut to bring everything back the way it was. And that's a look at how GLBP can, by default, do load balancing for us. It's going to do round-robin load balancing by default, and we saw that we could adjust that with our weighting. In fact, we could even have weighting work hand-in-hand with tracking. We could do object tracking, and we also saw that in addition to all this load balancing, it's going to give us redundancy. We saw that if we shut down the interface of Fast Ethernet 0/0 on R2, then router R1 started servicing the virtual MAC address that router R2 had been servicing.